Building a retro-inspired keyboard from scratch, part 2. Let's get started. And now a quick message about PCBWay.com, my favourite PCB manufacturer, who help make these videos possible by sponsoring them. Get your project going with PCBs starting from just $5 for 10 boards. And with the new multicolour silk screen, your boards will look like artwork. PCB prototype the easy way with PCBWay.com. Still being quite new to hot air soldering, I wanted to use this method to solder the diodes in place. What I found the most tricky, however, was actually seeing the line on the diode. Even with the bright light of the microscope, I found it quite challenging to actually see the line. After soldering the diodes in place, I then double checked the orientation of each one using a multimeter set to its diode test mode. And I'm glad I did, as it highlighted a bad solder joint that I needed to reflow. Some flux, solder paste and heat later, and it was all fixed. Next was the boot select switch. I tried rather unsuccessfully to hot air solder it, and as you can see, I ended up melting the plastic a little. So I desoldered it, cleaned up the pads, and then hand soldered another one in place. I then moved on to soldering the PGA 2040 in place. An issue I came across was that the plated through holes in my design were too small in diameter for standard pins, so I ended up stripping some single core copper wire and using this for the pins instead. I also had to do the same for the USB-C breakout board. Here's a close-up of the PGA 2040 and the USB-C breakout board. And here I think the small size of the PGA 2040 is really highlighted when shown against the size of the footprint of a single switch. Next, I found my second error. I had forgotten to take into consideration the 1.6mm thickness of the breakout PCB that the USB-C connector sits on. This meant that I needed to mark out where the USB-C connector would hit the faceplate and then using a Dremel, grind out that section of the PCB, taking care not to grind right through the board. This was the result, and it came out much better than I anticipated. The next task was to insert the keycap stabilizers, and as I did, I also gave them a little lubrication. Then came the switches. When inserting these, it's essential to pay attention to the orientation or they will not fit into the main keyboard PCB. I then carefully checked that all of the switch legs were vertical and any that were bent I straightened back out. Aligning the main keyboard PCB was quite tricky as it only takes one switch leg to be slightly off vertical and it will get bent and not go through the hole. But with a little care and patience it went on okay. I then added some nuts and bolts to hold it in place. The next step is super important. Before I began soldering the switches, I checked and double checked that all switch legs were poking through the PCB, as once soldered in place, the board would be extremely difficult to desolder and remove again. As soon as I was happy that all the switch legs were poking through the holes, I set about soldering them in place. Next, it was time for the keycaps. I then attached the bottom PCB, and it was now time to set about preparing the firmware. I used QMK Firmware in my keyboard, which sped up the development time as I didn't need to write the firmware from scratch. To use QMK, you download the software to your computer, modify some configuration files based on your keyboard layout, compile the firmware, and then upload it to the microcontroller in the keyboard. Select Setup and then your operating system. I'm using Windows, so with this tab selected, I'll download the prerequisites. This link takes you to their GitHub page. And here I'll download QMK_msys.exe. And I'll also download the SHA-256 hash so that I can verify the file integrity. Once downloaded, open the hash in Notepad. Here is the SHA-256 hash of the executable I just downloaded, so next I'll generate the hash of that file and compare it to this. If they match, then the file integrity is good. Open Terminal, CD to the download location, then list the folder contents to see the file names. Next, run the command get-file hash, then a space, and then the file name. Notice I didn't type the entire file name. That's because of the handy autocomplete feature in Terminal, where you can start typing a file name and then just hit the Tab key to complete it. The command returned this hash, which, when compared to the hash in Notepad, is identical, so the file integrity is good. Install the downloaded executable. During the installation, I left all of these settings set to default. You'll need some way of editing the configuration files that QMK creates. Whilst you can use Notepad for this, I do prefer to use Microsoft Visual Studio Code. This is a free download from Microsoft and the link is in the description. Right, run the executable and install it. I left these options set to default. Now we're ready to run QMK, so from the Start menu, open QMK msys. The first time you run this, you'll need to run the setup command, which is QMK space setup. Select Y to clone the firmware. This initial setup and cloning did take quite some time to complete for me, and I've sped it up for this video. Next, you need to create the comp files specific to the microcontroller you are using. This is done by running the command qmk space new dash keyboard. At keyboard name, you define the file path and name of the keyboard. So I'll save these comp files in a folder called iNimbleSloth. And I'll give the keyboard the originally well thought out name of the keyboard. Then enter your GitHub name, then your name. This next choice is a starting point for your keyboard layout. It saves time to choose one that is as close to your design as possible. So in my case, I'm going to select number 21, as it is an ISO layout, which is what I'm using for my design, and it has 96 keys, which is a little more than I'm using in my design, but I'll edit the comp files to drop the excess keys. Then you need to select the appropriate microcontroller. I'm using the RP2040, so I'll select number 37. The next task is to update the comp files to match my design, and the line above shows the location of the comp files. To edit the comp files using Microsoft Visual Studio Code, open Terminal and navigate to the location of the comp files. Then run the command code space full stop. This opens all of the comp files in that folder into Visual Studio Code, and yes, I'm going to trust the authors of this code. There are two main comp files that need to be edited. This one, called keymap.c, shows the layout of the keys in their row-column matrix. And this one, called keyboard.json, is what is used to define which GPIO pins on the microcontroller will be used for each row and column, along with defining the matrix. And there's actually a third file, conf.h, but you'll only need to edit this if you want to add a caps lock LED, and I'll show you that later on. So I'm now going to jump into the comp files that I used for my actual keyboard firmware. One thing to note here is that the name of this JSON file is different. Without looking into it any further, I can only assume it is down to the comp files being created by an older version of QMK than I just previously demonstrated. So here you can see the manufacturer name, keyboard name, maintainer, and microcontroller, which were all defined when running through the new keyboard script. Then you'll need to define the matrix pins. Cast your mind back to my last video where I created this diagram, which defined exactly which GPIO pin on the microcontroller would connect to which row and column. It's then just a case of running through and updating the comp file to match your diagram. So the first column is GPIO pin 2, then the next one is pin 4, then the next column is pin 6, and so on. Next we scroll down a little to layout. My design uses a layout of 6 rows and 17 columns, so update this according to your design. Then you'll need to update the matrix address, that's the one in the square brackets, and you'll also need to update the X and Y coordinates for each switch. So again, casting your mind back to my previous video when I created this image, I have the matrix address shown in purple, so that's a simple row column address. This key is matrix address 00, so that's row 0 and column 0. Then we have row 0 column 1, column 2, and so on all the way through to row 0 column 16. And then it's the same for each row, row 1, row 2, row 3, row 4, and finally row 5. So to reaffirm, the purple numbers on my image directly translate to these matrix addresses in the square brackets, so you'll need to amend, add, or delete lines of code here to match your keyboard layout. So all of these beginning with 0 are on row 0. Then this key, which has the matrix address 10, is here on my layout. Then I have the XY coordinates shown in blue, and remember in the last video I got the XY coordinates from keyboard-layout-editor.com, and you'll see the XY coordinates down here for each key that you select. So selecting the next key, we can see the XY coordinates as X2, Y0, and again these are entered into the comp file. Let's take a look at one more example on another row. So for the E key, we can see X 3.5, Y 2.5. Just checking my drawing, we can see that the E key is at matrix coordinate 2, 3. So in the comp file, if I scroll down to position 2, 3, you can see that I've entered the XY coordinates as per keyboard-layout-editor.com. So you'll need to do this for every key on your design and then save the comp file. Then, once completed, you'll need to edit the keymap.c file. The keymap defines what each key will do. The keys are arranged as per their row column address, and their function is defined with kc underscore and then the key function. So in the case of this key, at matrix address 00, that's kc underscore esc for the escape key function. The space key has a matrix address of row 5 column 6. Back in the keymap file, you can see that the space key is on row 5, so 0, 1, 2, 3, 4, and 5. Then we have column 0, 1, 2, 3, 4, 5, and this is column 6. And the space key function is defined with kc underscore spc. So if I scroll across to the right, you can see that I've completed this for all of the keys on my keyboard design. You'll just need to do the same for your layout. Right, since my design has a caps lock LED, I need to edit the config.h file. I added this line down here to define the caps lock LED as GPIO pin 23 on the microcontroller. I also added a couple of comments to remind future me exactly what this line is doing and a helpful tip about the voltage output from the GPIO pin. Before closing Visual Studio Code, ensure that you save all of the conf files. Now it's time to compile the firmware, so head back on into QMK and run the command QMK space compile space -kb space the file path, so for me that's iNimbleSloth, / and the keyboard name, so for me that's the keyboard. Then space -km space default. Compiling the firmware did take a little time, so again I've sped this up for the video. Once compiled, you'll receive a message saying that your firmware has been copied to the QMK Firmware folder. On Windows, that's in the user folder and then QMK_firmware. Then scrolling down a little reveals my firmware. It's now just a case of flashing this onto my keyboard. Depending on the microcontroller you have chosen, this process may differ. What I really like about the RP2040 is it's super simple to flash. Just press and hold the boot button as you connect the keyboard to the computer's USB port, and the RP2040 will boot as a USB drive. And then flashing the firmware is as simple as dragging the firmware onto the USB drive. So checking in Windows settings now shows my new keyboard attached, and here it is, the keyboard by iNimbleSloth. The only other thing you might want to do is raise the rear of the keyboard up slightly, so that the keyboard sits at an angle. For this, I 3D printed a couple of wedges, and I used some double-sided tape to attach them to the underside of the keyboard. I then stuck rubber feet onto the wedges and the front of the keyboard. Things that I would do differently if I was to design and build this again. First off, I would probably take the microcontroller, and instead of having a through-hole microcontroller on this second board, I'd go and have a surface mount one on the rear of the board. If I needed to do any fault finding or change that microcontroller, then it just becomes a case of taking the rear PCB off and you've got access to the microcontroller. As it stands, I wouldn't be able to do any modifications or fault finding very easily because the microcontroller is sandwiched in between the top two boards. The next thing I would probably change would be the USB socket here. So I would probably get this so that the USB-C connector is directly surface mounted to the board in the middle there, rather than have a breakout board. Other things that I would change, I would make the board slightly smaller, I think. Do away with this top part where I've got the microcontroller underneath, and possibly place the microcontroller in this sort of area here where there's plenty of real estate on the board. Another thing I'd possibly consider changing would be the way that the switches are held in place. So at the moment, the switches are placed through the switch plate and then they're soldered directly onto the middle board here. I probably would look at some kind of socket, so you can get the sockets that the switches can be placed into, and that way the whole keyboard could be pulled apart should it ever need to have any work done in the future. Another thing I'd think about would be possible cases. So I like the idea of building the whole thing out of PCBs, but it would also be nice to have a kind of a case. Now, I was thinking something along the lines of this clock that I'd previously made. Okay, I haven't done a video on this, but what I did here is I just took a solid piece of wood and routed out the space here for the PCB. I think that would look quite nice for the keyboard as well, to have a nice piece of wood. You could stain it, varnish it or whatever, and drop the keyboard PCB into there and fix it in place. I think that would also look quite nice. So I'd love to hear your thoughts on my keyboard design, what you would have done differently, what you would have done the same. Have you any suggestions for improvements? Thanks for watching. Subscribe and like for more videos like this. Click here to see part 1 of this video. Click here for what YouTube thinks you will enjoy the most next. Until next time, take care.